sure is so today we are mostly going to deal with displacement function. Sometimes it's written as S of t. The function S of t, displacement, is dependent on time, and displacement is denoted by S, or sometimes we could even write X of t, stressing the fact that displacement is nothing more than the coordinate of the object at a particular time. So S of t or X of t, basically the same thing, meaning the coordinate of an object or a particle, some kind of particle at a given time. And the thing is that, first of all, let's say that the time is always greater than or equal to 0, because 0, time equals 0, will be the starting moment of the motion. We will also assume that the motion happens in one direction, so it's a straight line motion. It could go back and forth, so the directions could change, but only on that straight line. So we are assuming that we have the line of coordinates S or X, depending on how we denote the displacement. We have somewhere the starting point of the coordinates, which is not necessarily the starting point of the particle or of the object that is moving. But at least it's the starting point where we start counting the coordinates and displacement. So the initial displacement, the coordinate at the time moment 0, time is 0. It could be here, but it could be somewhere else. So it's simply some point that is set as the starting point, the origin of the coordinates. And then this object is moving along this line, and its coordinate is some kind of function dependent on time. And then usually we are also given units of distance and units of time to describe this movement, to describe this motion. And sometimes we start with the displacement function x of t, and we are required to consider the velocity, and we are required to consider the acceleration. So if we know the law of motion, so if we know the that's why you don't hear the noise you're making, probably. Yeah. You could walk in a little more quietly, because it's just okay. If the others don't object, then who am I to object? Okay. So the velocity, in a similar manner to what we say, the derivative of a function is actually the rate of change of that function. So if we derive the displacement function, we basically get the rate of change of coordinate. What's that? That's the velocity. So the velocity is obviously the derivative of the displacement function. Acceleration is the rate of change of velocity, which means it is the second derivative of the displacement function. That would be the simple part. If you are given the displacement function, then you can be happy because you can find the velocity and you can find the acceleration, and you can actually find the distance traveled from the function itself. But in this part of the course, we are basically beginning with the velocity function, and we will have to find the displacement according to this velocity function. So we are sort of starting from the middle, dealing with integration, and going to get the displacement function. So there are some things that should be understood. So first of all, this will be a limited topic. We are only going to consider a straight line movement, nothing more. Secondly, velocity and speed is not the same. So basically you know that there are different words in English which we can use to describe this thing: speed, velocity, rate. So basically velocity is the most accurate description of this change of coordinate, because velocity takes into account the direction. So sometimes we might even talk about velocity vectors if we have a plane and, for instance, an object moving along a vector. So remember the direction vector of a line. So we might consider this not the direction vector, but the velocity vector, and the parameter lambda that we had could be turned into parameter t for time times the velocity vector, still going on with the equation of a line. So velocity involves direction. In this case, if we are only having a simplified movement only along the same line, and the velocity might change. So the velocity includes the absolute value and it includes the sign. So we will say that the velocity is positive if the object is moving in the positive direction, and the velocity is negative if this object is moving in the negative direction. What is speed then? Normally in physics we can talk about speed, and when you drive a car you still talk about speed. What is the difference between speed and velocity?
Vector.
So velocity is a vector, or at the very least, in this case, a number complete with a sign, positive or negative. But the speed is the absolute value of velocity. So for example, if my velocity vector is 6, 8, something like this, 6 and 8 meters per second, so it moves every second, it moves 6 meters horizontally and 8 meters vertically, for example. In other words, by a vector like this, then the speed, the actual speed would be 10 in this case. The absolute value, the length of this vector, the absolute value of the velocity. That's in case of vectors. That's in case of vectors. In our situation where the velocity is simply a number with a sign, positive or negative, the speed will be still the absolute value, the modulus of the velocity. So if I talk about speed, and I don't have any abbreviation, I don't have any specific notation for speed. Speed is the absolute value of the velocity. Speed is the absolute value of the velocity. Why is that important? Because we will also have two very specific different things. One thing is find the coordinate at a given time moment, find the coordinate of this particle according to the law of motion, find the coordinate of this particle at any given moment, or find the distance traveled. So find the displacement or find the distance traveled. And that's again a big difference, because if the velocity changes direction, then after 5 seconds, so if we simply look at the coordinate after 5 seconds, it would be, well, the value of the coordinate according to the law of motion. If we are talking about distance traveled, you see the distance traveled is different. The distance traveled is greater than the actual coordinate. So we will be mostly interested in distance traveled for different particles. And this is what we are going to consider. Alright, so now if the velocity is the derivative of the displacement, how do we find the displacement if we have the velocity? Yes, how do we integrate it? Yeah, well, obviously, if we have that law, if we have a formula, then of course we find the integral, the primitive function of that. But what about the definite integral? What about the boundaries of integration? What about the boundaries of integration? That would be the displacement. the difference of coordinates at the beginning of this motion and the end of this motion. How do we find that? So obviously, yes, we have to integrate velocity by t. So in this case, time will always, or in most cases, denoted by t, and we have to integrate by t, obviously. So if we want to find the displacement, then obviously we will have to consider the starting moment and the ending moment. So this integral gives you the displacement between these two moments of time. For example, if at some moment t1 the object is here and then it moves this way, that way, well, changing the direction, for example like this, and this is the coordinate at the time moment t2. So for example, this would be s at t1 and this would be s at t2. So what this integral would give us directly, like that, would be the displacement from this point to this point. What is the displacement? So it will be obviously minus something, negative displacement in the negative direction, from the starting moment to the ending moment. However, what happens if I ask you to find the total distance traveled? So if you have a car and you drive back and forth again along a straight road, then obviously the distance is important because you are wasting the fuel, whatever the fuel is. So how can we do this? What do you think? How do we find the distance traveled?
Area?
Area?
No. Volume. When you separate it.
We have to do separate time segments. We have to do separate time segments. For example, we need to find the moments at which the object, the particle, the car, the train, something else, changes the direction of movement. We have to find those moments somehow. We have to find the coordinates here at these time moments. And then basically you have to find this distance, this distance, this distance, and add all these distances together. But of course, the time period when we are moving in the negative direction, obviously the displacement would be negative, so we have to take the absolute value. In other words, to find the distance traveled, so this would be displacement. The change of coordinate between these two time moments. Now, if I want to find distance traveled, for example, in this case where we have 3 significant segments of time, so this is the first change of direction, obviously s of t something. Okay, t3 and in this case, and this would be a very special place again, t4, time moment t4. So what we have to do is now, sorry, these are not in order now, those time moments t1, t2, t3, t4 are not in order because the starting moment was starting moment was t1 and the ending moment was t2, so I had to put t3 and t4 in the middle. So what we have to do in this case is, obviously the distance traveled here, which is the same as the absolute value of displacement. The displacement is negative, but the distance traveled for this segment is, obviously distance traveled is always positive. So I could write the absolute value of the integral from time moment t1 till the time moment, obviously this has to be t3, of the velocity function, absolute value, plus I'm writing absolute value everywhere for all 3 parts, because in other situations, obviously, you might have 1 positive and 2 positive and 1 negative displacements and so on and so on. So what matters is, we have to split the time into parts, the time into parts according to the direction of movement. the direction of movement, so velocity positive or velocity negative. And then we have to find the distance traveled in each of these parts. Distance traveled means absolute value of displacement, because displacement could be negative in the negative direction. And then of course add all these parts together. So the second part would be from time moment t3 to time moment t4. In this case, again, the same velocity function integrated, plus finally from time moment t4 to time moment t2, again the absolute value of this integral, integrating velocity dt. So this is what happens. So please don't get confused, this belongs to the upper integral.
One question.
Yes, just a moment. So this belongs to the upper part. Yes, question?
You said if we're going into the opposite direction, meaning that would be minus, no?
The displacement, yes. Displacement, yes. And that's why I'm putting on these absolute values. Displacement will be negative if I'm going in the opposite direction, but by putting absolute value sign, by putting the modulus on it, I make it the distance traveled, regardless of the sign. We are only concerned with the distance traveled. So I put on the modulus signs because that makes me ignore the sign of this. So without the modulus, it would be the displacement between the two time moments, starting here, ending there, or starting there, ending there. But if I put the absolute value, if I put the modulus on it, it means only the distance traveled. We are not being told the direction. We are not concerned with the direction. And for these distance travel, for these distance problems, the important part is exactly that. How to split this whole process in time segments having the same direction of travel. Just like that. So now, if you look at the paper, the signs of velocity and acceleration, and what happens everywhere. So a little bit of interpretation of those darker boxes. So if the coordinate equals 0, if s or x of t equals 0, it means the object is at this point, at the point coordinate equal to 0, regardless of whatever time it is. If the displacement is positive, then the object is to the right of the origin, and if it's negative, then it's to the left of the origin. Now, signs of velocity, if the velocity is 0, it means the object is still for the moment. For instance, if before it has been traveling in the positive direction, slowing down, stopping, and then starting moving in the opposite direction. So velocity equals 0 means it is instantaneously at rest. At that moment it's stopped, even if it's just really for a split second or less. Instantaneous.
Or maybe it's going, like the speed is going negative.
So if the speed is if the velocity, not speed, velocity. If velocity is negative, it means we are moving to the left in the negative direction. If velocity is positive, we are moving in the positive direction. Acceleration. If we have a positive acceleration, it means velocity is increasing, but actually that means if we are traveling in the negative direction, but the acceleration is positive, so the direction of acceleration is opposite to the direction of velocity. It's slowing down. The speed is decreasing. The velocity is negative, so we are moving in that direction. The acceleration is in the opposite direction, so this object has to be slowing down. We have to be very careful because acceleration also has a sign, positive or negative. It also has a direction. So if acceleration has the same sign as velocity, they are both going in the same direction, then the speed is increasing because acceleration is boosting the velocity, the speed. If acceleration and velocity are going in opposite directions, the acceleration is working against the velocity, so it's slowing down, the speed is decreasing. So that's the difference. Velocity is increasing or decreasing strictly according to the sign of acceleration. If acceleration is positive, the velocity is increasing, and if acceleration is negative, the velocity is decreasing, meaning going more in the negative direction. But the speed, the actual speed of motion, depends on the change of speed of the motion depends on the directions, the relative directions of velocity and acceleration. If they are both going in the same direction, it means the acceleration is boosting the speed. If they are opposite, then the acceleration is breaking down this particle. So the speed is decreasing. So there you see there are important differences between velocity and speed and between displacement and distance traveled. Important differences. All right. So what we are going to do is we are going to draw two diagrams basically for this type of problem. One diagram will be for velocity because we need to see we will need to see the sign of velocity, whether this object is moving in the positive direction or in the negative direction. And that will be on the time axis. The same kind of diagram can be drawn for acceleration to decide whether it's positive or negative. And then the second diagram will be something like this, where we will show the direction of the movement. Even though we are not moving along the axis, we will show the directions above those axes, above this one axis. We don't have two. Okay, let's have a look at that example. So the velocity function is given, and it is t squared minus 3t plus 2 meters per second. So this means that time is in seconds and distance coordinates are in meters. So let's have a look at what is going on there. First of all, let's find at which time moments this particle or object changes direction. That happens when the velocity is zero between plus and minus signs. So one thing we have to do is find at which time moments the velocity is zero. We can find these.
This is changing of direction?
Yes. Velocity, well, it has to stop before going back. So at that moment, when it's changing direction, the velocity is obviously zero because it stops and starts going back. So this is, by finding the zero velocity moments, we actually find out at which time moment the particle or the object, 1 and 2 such time moments. So let's have a look. So remember that time starts at zero. We don't have negative time. We don't have negative time. We can't have negative time because if the movement begins at time zero, then before that, nothing is of interest to us. So we can see that this is the time axis. So actually, I do that like this. Time axis. So at this time moment, at 1 and 2, the velocity is zero. Now we have to figure out the signs of the velocity. Signs of velocity. So the sign of velocity, obviously, for very large t values or for t values close to zero. If t values are very close to zero, then the velocity has to be positive, and if the t values are greater than 2, then the velocity is positive, and between 1 and 2 it's negative. How do I know it? High school stuff, first semester stuff, Math 1 stuff. This is Math 1. You have to know, this is a quadratic function, the graph of the quadratic function is a parabola. This means the parabola would have ends up, so it's positive, negative, positive. You have to be able to solve quadratic inequalities since 9th grade or so. Okay, so this means that the movement goes like this. I'm not going to draw these slant arrows like we did for simple derivatives, because in this case we are simply confined to the single axis. It's enough that I can show this. So if necessary, we can also find the acceleration by deriving this function. By deriving this function, we can find the acceleration. So the acceleration is the derivative of velocity, and that would be 2t minus 3. And so we can actually find the starting acceleration. We can find the moment where the acceleration is 0, and so on. So if necessary, we can check the signs of acceleration. So for acceleration, the same thing, a of t, 0 moment, time. Acceleration is 0 at time moment, 1.5. So it's 0, 4, t is 1.5 there. Before that, so if t is greater than 1.5, the acceleration is positive. If not, then it's negative. So now we can actually analyze the situation. We would say when the speed is increasing and when the speed is decreasing, and when the velocity is increasing and when the velocity is decreasing. So obviously, if the acceleration is negative, I say up to in the first 1.5 seconds, the velocity is decreasing. After the first 1.5 seconds, the velocity is increasing. The speed, though, I can say that from time moment 1, 0 to time moment 1, in the first second, velocity and acceleration have opposite signs. So the speed, not the velocity, but the speed is decreasing, it's slowing down. After the first second, so between the first second, after the first second, for half a second, the acceleration and the velocity have the same sign. So this object is picking up speed. Now, after 1.5, time moment 1.5, the velocity and acceleration again have opposite signs. So that means the speed is again slowing down, so it's braking again. And then it stops momentarily, and then it starts increasing. So this means that we have 1, 2, 3, 4 distinct periods of time with different behavior of this object. I mean the physical behavior, speed-wise. So we start with slowing down, then picking up speed, then slowing down again, and then picking up speed again. But the velocity is positive, negative, positive. Decreasing velocity and increasing velocity, which actually, if we are interested in how we feel inside that car, then obviously we're more interested in speed, because we feel strange when we brake fast or when we accelerate, which is basically why people get car sick. This rapid change in acceleration, actually. All right. So what can we do next? Now we can calculate or find the displacement. How far does P travel in the first 4 seconds, and find the displacement of P after 4 seconds. So the displacement of P would be obviously the coordinate of P, or the displacement obviously is this displacement between the starting point and the starting moment and the ending moment. So, all right, let's integrate. So the displacement of this object will be obviously the primitive function t squared minus 3t plus 2 dt, basically. At any given moment, it would be t cubed over 3 minus 3t squared over 2 plus 2t plus some constant. And this constant is the location of this particle at the starting moment. When time is 0, you can see when time is 0, C actually means the starting point, the starting position. And if we don't know C, we don't know where exactly this object started the movement. So we can just assume that it happens somewhere at the point with coordinate C, whatever it is, positive, negative, 0, something. So this is now the coordinate line, the distance or the location line, the displacement line. So for this, where we want to figure out the signs and understand the motion, we have to use the timeline. This is the timeline with respect to time. We look at the signs depending on time. In this case, we are going to analyze the motion of this particle coordinate-wise. So this axis, this line actually shows us the coordinate. So we don't know where, it's just C. Now, we could, of course, find the coordinate at time after 1 second, after 2 seconds, after 3 seconds, after 4 seconds. But if we are only interested in the displacement for the first 4 seconds, then what we need is we have to find the location after 4 seconds. So, all right, so S of 4 is 64 over 3 minus 3 times 16 over 2 plus 8 plus C, which is something minus 24 minus 16, and that would be 21 and 1/3 minus 16. That would be 5 1/3 plus C. Again, because I don't know what C is, but I know that the displacement during 4 seconds, the resulting displacement is from C to 5 and 1/3 plus C. Obviously, movement to the right. The displacement is positive. So the displacement is 5 and 1/3. If we compare the starting point and the end point at the time moment t is 4. So this happens when the time is 0. This coordinate we have when the time equals 4. We see the displacement. The displacement is 5 and 1/3 in the positive direction. Now, how to find the distance traveled? Let's see if this writes somewhat better. I'm going to erase this part now. Okay, now let's consider the distance traveled. So at the time moment 0, we can say that t equals 0, the particle is there. The first moment when it changes direction is time moment, we found it, 1. So now I should find S at time moment 1. Put 1 in there, so it becomes 1/3 minus 3 halves plus 2 plus C, which is 1/2. 1/2 plus 1/3 is 5/6 plus C. So that's somewhere there. So it's C plus 5 over 6. This is at time moment. This is at time moment 1 second. After 1 second, we are there. Now, remember that after the first second, the velocity becomes 0 and then it starts moving in the opposite direction. So now, and the second moment of change of direction happens when time equals 2 seconds. So now, the second time change. I choose 1 here, not simply because I want to know where it happens to be after 1 second, but because I want to know where it changes direction. Because I know that at this moment, it will change direction and start moving in the opposite direction, to the left in this case. So the second change of direction happens at t equals 2, because those were the two zero velocity moments. Now, what do we have there? 8 thirds minus 3 times 4 over 2 plus 4 plus C, 6 plus, minus 6 plus 4 is minus 2, 8 thirds is 2 and 2 thirds minus 2 is just 2 thirds plus C, okay, just a little bit. So now we are going backwards to 2 thirds. The actual scale, of course it doesn't matter. What matters is the correct order of the points. The correct order of the coordinates. So to this is time moment t is 2. So during the first second, this object moved from point C to point C plus 5/6. In the second, from time 1 to time t to time 2, it moves in the negative direction to the point C plus 2 thirds. And now, because this is the second change of direction, now finally no more changes of direction. Now I can find the location at the final moment. Actually, we have already found it. There it is. So we know that the coordinate after 4 seconds is 5 and 1/3 plus C. So it goes that way to the time moment C plus 5 1/3. And this is time moment T is 4. And now, when you look at this, now we can finally calculate the total distance traveled. It will not contain C because it will not depend on C, obviously. All those C terms will cancel out. So the first, we can now subtract this coordinate minus this coordinate. So the distance traveled here from this point to this point will be 4 and 2/3. So this distance is 4 and 2/3. This distance is 1/6, and this distance is 5/6. So it's 5 over 6, 1/6, so total 1, and this distance is 4 and 2/3, so it's 5 and 2/3 the total distance traveled. So now you simply have to subtract these coordinates to find the length of each segment and add them all up. You might notice that I didn't write all those integrals. So you can do this by integration. For instance, you could take that v of t, which is this function, dt, and integrate from 0 to 1 plus integral from 1 to 2, v of t dt, plus integral from 2 to 4, v t dt, and of course, now at this point, now that we have the motion diagram, we know that the negative displacement is the second part. So I can simply put the absolute value on it to make it positive. And now, distance traveled, distance traveled, distance traveled. So you can do it like this, or you can do it like this, in an open way. It is possible to write it as an integral and integrate, or this way. We are doing exactly the same thing actually. S of 1 will be the primitive function at 1. Yes?
After finding all the displacements, how you took the distance traveled?
I added up the distances in each part.
Only.
Add the length of this, plus length of this, plus length of this. Just make sure that you do not subtract anything, that you do not use negative numbers there. That's why I put this on there. The length of the first segment is actually this integral. I can write it as an integral, or I can find it in a simpler way. I can write the second part as an integral, or I can write it in a simpler way. And I can write the third part as an integral, or I can simply find it this minus this. So the end point minus the starting point. But if you look at the diagram, you will always know which number to subtract from which number. Of course, we subtract the right hand end point minus the left hand end point. We do not even concern ourselves with the direction of motion, because what we need is we subtract the greater number coordinate minus the smaller number. The greater number minus the smaller number, the greater number minus the smaller number. Then you don't have to worry about integrals. Well, the problem is that you need to integrate anyway, because if you are given the velocity function, you need to find the displacement function, so the integral is necessary. But you can write it once, simply to find this function, or you can write this immediately, but to write it like this, you still need to know those time moments when the movement changes direction. Okay, so now exercises 1, 2, 3, 4, 5, 6. I believe probably number 1 is very simple. You can leave it for home for revision. 2, you can leave it for revision, and we can actually look at 4, 5, 6 for example. Those are more interesting. Okay. Start looking at those and...
One question.
Yes.
What is the end result of this?
The result? Oh, you want me to count? Okay, 5 1/3 minus 2/3. I think the result was 5 2/3. So for the...
6, 5, 6.
Okay, 5 over 6 plus c minus c, that's the first part, plus, now the second part, 5 over 6 plus c minus this coordinate, that's 2/3 plus c. And the third part will be 5 1/3 plus c minus, again, 2/3 plus c. Simply subtracting those coordinates, you can see that all the constants, all the c, will disappear. So these cancel out, these cancel out, these cancel out, and you simply calculate. So it will be 5 over 6 plus this difference is 1 over 6 plus this difference is 4 2/3. So this is 1 plus 4 2/3 is 5 2/3. That's the total distance traveled. And it's not much different from the displacement this time. Notice the displacement is 5 1/3 plus c, or the displacement is 5 1/3 if we only compare the starting point and the end point. And this is 5 2/3. Why? Because this doubled extra part is very, very small, from 2/3 to 5/6. It's 1/6 and 1/6. So altogether, 1 over 6 in one direction and 1 over 6 in the other direction, and then we move on from that same point onwards. So 1/3, this part is altogether only 1/3. Total 1/3, this extra part. So that's why it's not so different from 5 and 1/3. Because here the displacement 5 1/3. The displacement during the during the first 4 seconds, and here 5 2/3. Because this is comparatively very, very small. But it's not always like that. Sometimes it might be greater, longer distance. Okay. Number 3, then. Yeah, we have velocity function given. Find the total distance traveled during the first 3 seconds, or between the first and the third second. The total distance traveled. To find the total distance traveled, you need to find at which time moments we have direction change. So we need to see at which moments this object, particle, at which time moments this particle stops before reversing the movement. So we do need to find the zeros of velocity.
This was the same like you. So.
It's very similar, yes. It's very similar.
How about the number 4D?
We will do this. We will get that far. We will get that far.
Looks like limits, no?
I only want to point out one thing about number 3. We have a cubic function there, 16t minus 4t cubed, and that's the velocity. That's the velocity. X derivative, if you notice. That's the velocity. To find the 0 points, the 0 or the moments, we would need 4t, 4 minus t squared. So the 0 velocity, we have at time moment 0, at time moment minus 2, and at the time moment 2. This can be discarded because we don't deal with negative time. So we know that the velocity is 0 at the starting moment and at the time moment 2 seconds, after 2 seconds. So please make sure that when you are considering this motion, we are not really interested in negative time. We only look from the time moment 0 forward. The rest is pretty much the same as the example I showed you. That's why I'm not going to solve this completely. And well, if you have questions, then you will ask. Now the next part to consider will be exercise 4. D. Discuss velocity as t tends to infinity. In other words, we have to figure out what happens to this, it's a particle, what happens to this particle as time goes on and on and on and on. So we have to understand this function. It's an exponential function.
So it will infinitely move upwards?
Well, it will not accelerate infinitely. Let's have a look at this function. V of t is 50 minus 10 e to the power minus 0.25 t. So first of all, t is only positive. If t tends to positive infinity, then the exponent of e tends to negative infinity. What is the exponential function like?
Now we're doing number 4, right?
Yes. I was asked about 4D, so I have skipped ABC, obviously, because we are interested in the understanding of this function. So first of all, I have to see. So if t tends to minus infinity, if t tends to plus infinity, then the exponent tends to minus infinity. So e to this power would obviously be, well, we know the exponential function. And now I am relying on your, I don't know to what extent existent knowledge of exponential function, but the basic exponential function, the graph is like this, and we discussed this last semester. So exponential function goes like this. Now if I have to multiply by minus 10, it means the exponential function goes like this. So it will be 10 times down, but multiplied by minus 10, then it becomes like this. And now if I have to move it 50 units up, well actually, I should have drawn with this negative exponent. I should have drawn it up the other way. So if this is minus t, which is not a good thing. Okay. I will sketch the exponential function. So if e to the power minus something, then the exponential function will obviously be, the exponential function will be decreasing. Now if I multiply it by minus 10, it starts looking like this, and then if I move it 50 units up, then it will look, well, like this. And because we have a horizontal asymptote at all times, then obviously the velocity will tend to some fixed value. It will be increasing, increasing, increasing. See, this will be becoming less and less and less, because when t tends to positive infinity, the exponent tends to negative infinity. E to negative infinity is 0. So 50 minus something very, very small, and smaller and smaller and smaller, which means the velocity tends to become 50. It might never become 50 actually, because there will be always this slight difference. For very, very large t values, this will be a very, very small number, but still it will be there. But we can say that the velocity approaches 50 as time goes on and on and on indefinitely. So we don't even need to discuss these graphs. It's enough to understand the exponential function to remember that. If we have the base greater than 1, then if the exponent tends to negative infinity, which it does, if t tends to positive infinity, the exponent altogether tends to negative infinity. So e to negative infinity becomes very, very, very small, positive but very, very small. So yes, we might multiply it by 10, but it's still very, very small. And if I subtract something very small from 50, it's almost 50. And the longer we go on, the smaller this part becomes. So the less we subtract from 50, which means as time approaches infinity or tends to infinity, the velocity approaches 50. And that's all. So that's the discussion. You don't even have to write limits. You don't even have to do graphs. It's enough that you look at the properties of the function, in this case exponential function. Okay, how do we show that the particle's acceleration is always positive? How long would it take for the particle's velocity to increase to 45 meters per second? And so on. So if t is 0, what is the initial velocity of this particle? If we have to talk about number 4, then let's start from the beginning.
40?
40, the initial velocity at time 0, 40. After 3 seconds, we could calculate a little bit. If t is 3, I should probably email you this.
It's infinitely, it's decreasing.
No, nothing to do with it. You have to put 0 there. Forget it. So,
34.
you have e in the power of 0.
I didn't say.
Is 1.
Yes. No, nobody signed. Nobody signed. Before I give this paper to you, I just counted, so that there are 34 signatures, I hope. I know that they didn't sign because I didn't give the paper. being the evil teacher. Goes to math 2. Okay, math 2. So I'm reminding you that next week, sorry, I'm away, but I do hope that we can get back our lecture time in the last week of May, so that we can complete the course. So I don't want to lose the time, so we'll have to work in the
We
last.
don't have next week the lectures.
You don't have math next week.
yeah.
Everything else is still on. It's just me who disappears.
We'll get the math.
All,
You
so
will.
both in Tuesday and Thursday?
Yes, both times. Both times. You will have them. I keep them on my mind.